This is your reservoir. I gave you the water oil touch point, okay? And I gave you the whole thickness of the reservoir is 100. Also, I gave you the curve that represents the saturation, we call it saturation profile with the capillary pressure, where here's the capillary pressure and here's the saturation distribution. Okay. If you look to the data, you would find I gave you also that this zone, what we call the transition zone, is 20 feet, correct? The free oil zone is 80. So you get the average porosity, average saturation for this 80 feet, then you calculate the oil initial place. Hey, this is the oil initial place of the free oil zone, period. What about the other 20 feet that I have here left? Okay, I gave you the distribution of the, or the amount of oil in the 10 feet here. It has 50% water and 50% oil, correct? So that's also an oil there. So you can take this zone by itself and you calculate the oil initial place, or the amount of oil that can be, the amount of oil that exists in this zone, and the amount of oil that exists in this zone, which is 90% water, means 10% oil, correct? You add all of these three together, that's the total oil exists in your reservoir. Now the argument, which, how many barrels of oil I will produce from this oil initial place, that's the question, okay? It depends on the natural energy of your reservoir, the deriving mechanism, that's what we're going to talk about today. Also, the technique that you're going to use after you deplete the natural energy or pressure of your reservoir, which is, could be water flooding, could be gas flooding. After that, you will have also remaining oil where you're going to use an EOR or enhanced oil recovery methods to extract the amount of oil. There's a term here we call it recovery factor. What is the recovery factor? The total amount you have in your reservoir, okay, that's N. How many barrels of oil you're gonna produce? That's NP. If you divide NP over N, gonna give you a percentage, correct? That percent represents the recovery factor. Your task as a petroleum engineer is to evaluate, to propose methods to increase the recovery factor. Okay? So before going to talk about the deriving mechanism and to talk about how many barrels of oil we produce, we should understand the classification of reservoirs. What you are, all of the materials that you are studying right now works only, it's a majority, 90% of the equations, concepts that you are studying in the school applied only for the conventional reservoir. Definition of conventional reservoirs based on permeability. Any reservoir has permeability, average permeability above 1 and above. We put that under the classification of conventional reservoir. We say we have a conventional reservoir. Why do we do that? Because this is the only term that we cannot control in the reservoir, correct? The ability of the rock to allow the fluid to flow from point 1 to point 2. We can control pressure drop, correct? Delta B, but permeability in the reservoir, that's the thing that we cannot control unless we're gonna I'm going to talk about the ways to improve permeability in unconventional reservoirs. I'm also going to talk about the deficiencies of these methods. Okay? So you should understand that I have two types of reservoirs, conventional and unconventional. What I'm studying there is applied only for conventional reservoirs. I know I have this. Okay. You go back to the picture, that your memory back to the picture I showed, where we calculate the oil initial in place and stuff like that. We can I'm not this. What about? Okay. We can, based on the natural energy in the reservoir, due to the deriving mechanism of that reservoir, we have a stage of the life of the reservoir. That stage of production called the primary production stage, where you can produce from 10 to 25 to 30% of the total oil you have in the reservoir. Okay? Then you might go further after your reservoir or your natural energy is depleted. You're going to go for a secondary recovery method where you're going to apply water flooding, gas flooding. You're going to maintain the reservoir pressure by injecting the produced water again. That's also a method. Okay? After you're done with these two, you go to the EOR method or methods or enhanced oil recovery methods. And this flow chart here, shows in details the steps that any petroleum engineer should follow to ensure the highest oil recovery. Okay? Natural flow, that's a natural energy. In some cases, you're going to have a problem. Your pressure can get the oil out of the formation to the well pool. Once your fluids fill the pipe, there's hydrostatic pressure will be formed, correct? At this point. If the hydrostatic pressure is above the bottom hole pressure, below this point, that's where you have to use an artificial method. You inject gas to the pipe to lower the density of the fluid. Once the density is lowered, hydrostatic pressure will be decreased, rho GH, correct? So you will help the pressure in the well bore to just push the oil up. That's gas lift. Or you set the pump and you start just sucking the oil out of the well. That's the process that you're going to follow. Once you finish with all of these, you're going to go with the secondary water flooding or pressure maintenance. By the way, water flooding and maintaining the pressure by gas injection, these two different concepts. This one, you inject water flooding, you inject the water in the oil zone to display the oil toward the producer, okay? While here, you inject water in the aquifer, which supports the pressure, which is the water zone, which supports the pressure of the reservoir. So these two are different concepts. After you finish with this, you have to select one of these methods to get more recovery. No one can produce 100% or have a 100% recovery value. Trust me. You can get 60, 70, but you will have remaining. You will have something there. Even after the EOR methods, you will have some oil left. So that's why the reserves, have you heard of this term before? The reserves of countries is evaluated based on the amount of oil that can be produced, not the total initial oil increase. Okay? That's why when we discovered the shale oil reservoirs, the reserve of US went up because we had potential there and we can produce it. Okay? Let me talk about the unconventional reservoirs. The issue of unconventional reservoirs is the permeability. Permeability measured in nanodarcy. You know what nano means? 10 power of negative 9. 0.0000. Read down the other zeros value. That's the ability of the rock to allow the fluid to flow. So if you drill a well in shale oil or shale gas reservoir, you get your rig, put your rig, you drill a well, you apply the max pressure drop. Reservoir pressure 6,000, bottom hole pressure is 100 psi, 14.7. Are you going to have flow? No. If you go back to Darcy's law, there's K in top, correct? K and delta B are associated together. You have to have permeability, and you have, on the other hand, you have to have pressure drop. Now, you stop producing once the pressure drop gets to 0. That's what we term of depletion. Depletion means you don't have any pressure drop. The pressure in the reservoir is equal to the bottom hole pressure, delta B equals 0, no way to produce with the natural energy. That's the concept. So, what can we do? If we can stimulate the permeability of the formation that contains the oil, we can produce oil. That's the concept. That's where the hydraulic fracturing concept came from. We start just injecting the fluid with high pressure. That pressure is greater than the fracturing gradient of the formation. We create bads, cracks, anything. Call it whatever you want. We stimulate the permeability. But the disadvantage, it's okay. With using the hydraulic fracturing treatment, you can, all of the literature states that the recovery factor of shale oil, shale gas, that contains billions of barrels of oil there, is from 5 to 3%. So you have from 90 to 95% oil remaining in these reservoirs. Just, you have to say, wow. Means if you have 1 million, example, 1 million barrel, you can get only max 100,000. And 900,000 gonna be left there. Yes?
This one with the facts or without?
After the fact. The 10, the 5, and the 10% is I'm talking about after hydraulic fracturing treatment. See? That's my dissertation. Yeah, you working this down. Because when I read this, I said, okay, something needs to be done there. Because you have oil. Any new technology, any new technique you can come up, and you can approve it, industry will listen to you. Because you have a lot of oil remaining. The advantage of this method, let me put it this way. The problem of these reservoirs, you cannot use water flooding. You cannot use gas flooding. Why? Injectivity, formation permeability is 0. You push, no movement, but you're gonna create frac. So anything you imagine will not be applied if you're studying in conventional reservoirs. Yes?
Should that change for a zipper frac?
Yeah, you're still talking about fracking. Yeah, it's fracking. No EOR method. What you are doing is still in the same concept, fracking. This is what people do. They frack, after this frack, refrack again, same formation, to improve, to see if there's any frac closed, to open it again. So it's still in the same concept. So if anyone wants to do research, this is an area of research. The problem here, the disadvantage of this fracturing, hydraulic fracturing treatment, you are producing only from the fractured zone. That's the disadvantage. That's the only area that you are producing from, the fractured zone. You don't produce here, from here, from here, from here, from here, because there's no flow. Only from the zone that you framed. And I'm going to talk at the end of, or maybe in April, I will talk about the principles of these reservoirs. Okay, at least to have an idea about these reservoirs in details. This is the concept of water flooding. As I said, you just inject water in the oil zone and you display the oil, and it is area of research too. Why? Because if you look there, viscosity of water is different from viscosity of oil. You might have the oil, also the permeability, the homogeneity of the formation plays a major role here, because if you have high permeable zones and low permeable zones, what will happen, your water will flood only the high permeable zone and will leave the low, what we call the effect of heterogeneity in water flooding, or discontinuity, due to the difference in permeability. Different in viscosity also, you might have a fingering problem or bypassing. This is the oil, your water displacing the oil this way. If it get away from this oil, it might go to easy bath and leave the oil behind, and you get to the breakthrough where you start producing what you are injecting from the injector. What makes that different in viscosity is heterogeneity of the formation. That's where, if you have this problem, we go back to the EOR method, where we use polymer. We inject polymer to close or to seal all of the high permeability zones, to just leave one choice to the water, to display the oil that's in the low permeable zones. Okay, so let me conclude with this. You have formation. If you understand this concept itself, this simple concept that I'm going to talk about today, if you understand it, let me say you're halfway to be an effective petroleum engineer. If you have a formation, that formation of permeable, you drill your well, you do casing, put your producer pipes there, you perforate, you set the packer there. This is your initial reservoir pressure. That's 0.1, P1. You need, in order for the fluids to flow, you need to set low pressure point at the wellbore, correct? You understand what I'm talking about? These are the concepts. And once you apply that low pressure zone, okay, your wellhead pressure also must be lower than the pressure at this point. If all of these are applied, you're going to have flow. If the pressure in the reservoir is greater than the pressure in the wellbore and bottom hole pressure here, and the wellhead pressure is lower than the bottom hole pressure, you will have oil flowing from the formation to surface. If not, no way. And what makes this pressure maintained, or causes, or makes this, generates the reservoir pressure distribution, the initial reservoir pressure distribution, is the deriving mechanism, which is what we're going to talk about today. If you have high pressure, reservoir with high pressure, this one is controlled. You can control it. You can decrease it or increase it. But this is what I'm talking about when I said artificial methods. In some cases, you need to, if the hydrostatic pressure of the oil here creates a pressure higher than this point, no way for the fluids to flow, correct? So that's where you have to set valves in your pipe here in these valves, you're going to inject gas to lower density to help this poor pressure to push the oil. Now, if you want to fix this one and you want this pressure in the reservoir maintained, you have to think of, if you have a water aquifer, you need to think of injecting water in the water aquifer to support the pressure in the reservoir. Right? If you have a gas cap, you need to think about injecting gas to the gas cap to maintain the pressure here. So once you maintain high pressure here and low pressure here, you're going to have fluid flow. Okay? And that's why fluid course is a required course for petroleum engineers. Because it's a concept of fluid flow, or fluids flow, in pipes, in porous media, whatever. So, we have 6 deriving mechanisms that supports the pressure, that creates the pressure here in the reservoir, at this point. These deriving mechanisms are rock and liquid expansion, depletion drive, gas cap, water drive, gravity drive, and you might have a combination like cocktail. You can have gas cap and you have water drive. Gas cap from the top and water drive from the bottom. That's what creates the pressure in the reservoir here. You got that? Yes? Okay. Here is the description of each deriving mechanism, the rock and the liquid expansion. When you are in the formation, you have more that you have grains, pore space, under high pressure. Okay? Once you create a low pressure zone, what will happen? The fluids that's inside, it's like if we, 3 of us pushing this guy with an energy greater than him, his energy. Okay? So he cannot move, correct? Once we reduce the force from one of these sides, what will happen? He will move toward that scale. This is actually the rock and liquid expansion theory. Okay? And it should be happening under the depletion of the reservoir. Have you taken these before? Methods? You went through these before? Okay. Okay. So, a lot of literature talks about the ability of each mechanism, how many barrels of oil we can produce if we have under the natural or the primary production, before gas flooding, water flooding, or anything. A lot of literature, it depends on the history. Some of them say that solution gas drive can lead to 10 to 25%. Some of them say water drive from 15 to 60, and I have another literature says till 55. It depends on the size of the aquifer you have. If you have an active water drive or active aquifer where it contains a lot of volume of water with high pressure, that's maybe lead to the 60 or something. But there's something. There's this advantage of that. Here's the point. There is advantage of having a strong water, a strong aquifer. If you have a strong aquifer beneath your oil zone, this pressure here, if it's too low, and you have your aquifer here, this is water-oil contact, correct? High pressure, and you have low pressure here, what will happen? All of the water will start moving toward this low pressure zone, And that's where you're gonna have water cooling, and you start producing 100% water. Even though you have a good permeable reservoir, high permeability, but the management of the pressure is very, very important. If you have this issue, you might need to go to the use of one of PETR methods where you need to inject polymer to shut or to seal the whole zone here. Okay? And you maintain the pressure at this point to allow the fluid flow this direction. So anything you learn in reservoir engineering, any principle you learn from reservoir engineering, try to keep it in mind and to apply it when you get a job. Okay? Because you might come up with new methods, and I'm going to show you one of the things that I just wrote a comment on. You will see it later. This is the depletion derived mechanism. You have your oil, and in that oil you have a dissolved gas, so you have a single phase, and your reservoir is under saturated conditions, which is above bubble point. Once you open your well for production, pressure will go below bubble point and will lead to the gas to escape from the liquid phase.